into the feasibility of stochastic processes applied to formal grammars as a method of natural language generation by Daniel Hartgrove. Language generation is the name given to the software process of producing naturally written or spoken language. It is computationally expensive as it requires a lot of data analysis. Therefore, current solutions for NLG cannot be run on low-power machines, which severely limits the range of use cases. While developers could outsource to other LLMs like GPT or Gemini, these models cost money to use, and for large software, this cost could be prohibitive. NLG, back to its core concepts, I hypothesize that by merely analyzing the frequency of consecutive pairs of words, we can extract sufficient context to be used in other NLG processes. Because there are only a finite number of correct sentence structures, we can simply select a sentence structure and then apply this context data that we have extracted in order to produce sentences which are coherent and structurally sound. The algorithm works by generating a series of tokens using a grammar, an example of which is given on screen. The algorithm then consults a configuration file that it has loaded. The configuration file will have been populated by parts of speech tagging text to find relationships between words and their types. An example is given on the screen. The tokens are then processed in a queue. Because there's no data for the first token, a word is selected randomly. The only suitable determiner is the, and so that word is chosen and added to the return text. Following the algorithm looks for all instances of an adjective token that follows the. In this case, we see that we have quick and lazy, which both have a frequency of 1. These are then added to the lookup vector and the transition vector. The algorithm takes the bias of probability of selection into account and selects one of the words from the lookup vector. On this occasion, we have selected quick, which is then added to the return text. This process repeats until all tokens are filled, and then it is processed to make sure that the punctuation is correct. The output on this occasion is the quick brown fox jumped over the lazy dog. To evaluate the effectiveness of my algorithm, I ran an adapted Turing test using an online quiz. Each of the questions had 12 quotes, 6 of which were real and 6 of which had been generated by my algorithm. Users were asked to select which of the 12 quotes they thought were real. The ideal result was that users selected a roughly 50-50 split between the real and generated quotes. This test was then distributed online to a random population of anonymous participants, and I received 60 responses. The lack of available training data, training time, and the amount of data that can be obtained from a single novel being fairly small, the test itself was bottlenecked. However, on small data sets, we can conclude that the project is ineffective. As the scale of the data increased, although minimally, it was noticed that the algorithm performed better. Therefore, I believe that with a much larger data set, the project could be viable. To show off the concepts that my algorithm would allow for, I produced 2 proof of concept software demos to show off the use case of talking to an NPC in a game with randomized natural language to make it feel more immersive, and a Discord bot that could use the algorithm to produce text for a variety of reasons. However, in conclusion, I have determined that stochastic processes, when applied to formal grammars, are not a feasible method for natural language generation, at least on small data sets. Thank you for your time.